Thanks to the organizers for the possibility to give a talk today, this wonderful meeting. And well, today I would like to tell you something about the possibility to obtain a metric from asymptotically safe gravity, able to describe the so-called Planck stars. This is a project, a collaboration that I'm doing with my friend Gaetano Lambiase. We already published a paper and another one is on the pipeline. First, let me tell you something about just a brief summary of the approach of asymptotically safe gravity. Scale dependence at the level of the effective action is a generic feature of ordinary quantum field theory. In particular, in gravity, the scale dependence is expected to modify horizons, thermodynamics, quasi-normal modes of classical black hole metrics. And usually, in order to arrive to these modified metrics, there are three steps to be done in order to get these so-called ASG-BH black hole metrics. Of course, here we are building on the work of previous authors, particularly Reuter, Bonanno, Vectorix, Auressing, Totani, and many others that are works in this field from many years. The first step is to write down a scale dependence effective gravitational action. They are like these. G is the metric, G of k and lambda of k are the running Newton constant and the cosmological constant. Running cosmological constant. The cosmological constant may be here approximated to zero because we are interested essentially in local black hole metrics. And also it's important to introduce a dimensionless Newton constant which is linked to capital GK by this relation here. And the scale K is essentially the energy at which we are considering our theory, or if you like, the momentum. From the evolution of scale-dependent quantities governed by the Vectoric equation, from which equation we can derive an evolution equation for J of k, which is this object here, and once integrating for G of k, we can go back to the dimensionful Newton coupling, which is given by an expression like this. So clearly we have deviations at high energy from the standard gravity, because for very high energies the G of k goes to zero, while of course for small energy or small momentum transfer, the k, when k is close to zero, we recover the standard classical space-time, classical Newton constant and space-time. The second step, in order to arrive to an useful black hole metric, is to point out the link between the energy scale k and the radial coordinate r, so-called procedure of identification of an infrared cutoff, where essentially the result of this procedure is the fact that k of r it can be written in a form like this. Which is that essentially an energy scale is modified, is a kind of modified proper distance. It interpolates smoothly between the proper distance close to r equals 0 and infinity. Or if you like, for larger r, you see that k is inverse proportional to the radial coordinate, kind of Heisenberg relation. And once you plug this k back to the J of k, you get this expression for the running Newton coupling with this object here. Clearly, there is a quantum correction to the standard gravity. G0 h bar is just the Planck length squared, while omega tilde and gamma are essentially numerical constant to be fixed in some way, and we will see which way. Once you have these G of R, then the procedure, the ESG gravity approach, in order to obtain this renormalization improved classical Newtonian gravity or even general relativistic gravity, is to replace everywhere the Newton constant with the random constant G of R. So in particular, if we have a Lorentzian metric, spherically symmetric metric of this kind, you just replace the standard Newton with G of R here, and you get an expression like this for the lapse function of the metric. So this will be our ASG Schwarzschild metric. There are two important limits to be considered here for large R, and which means essentially low energy. We recover the standard Schwarzschild, therefore standard Newton essentially. While on the contrary, for at small r, which means large k, we have a couple of different situations according to the fact that either gamma is different from 0 or gamma is equal to 0. If gamma is different from 0, the core of this metric can be a de Sitter or an anti-de Sitter metric, so essentially, according to the fact that this quantity is positive or negative. On the contrary, if you have a gamma equals 0, you are going to a kind of conic singularity for a small r, so close by to the singularity. The nice thing of a metric like this, of course, is the fact that in the standard Schwarzschild you have an essential, an eliminable singularity r equals 0, and here they are cured, so to say, these two singularities. Okay, the problem is how to estimate these parameters omega tilde and gamma. As we said, the SG improved Newtonian potential can be obtained from the standard Newton by simply replacing the experimentally observed Newton constant G with a coupling G of R. We have clearly, once you have either you do this or you start from Schwarzschild and then you go to the equivalent to the low energy potential, and then in any case you get this expression for the Newtonian potential predicted by this ASG approach. You can expand this expression for large R, and you see clearly here the correction in respect to the standard Newton. The first correction is particularly important. Are all correction quantum-like due to quantum correction, so to say, because they all contain H bar. In particular, we are interested in this term of omega tilde. As I said, they are genuine quantum correction, genuine quantum nature, a correction of genuine quantum nature. And how can we fix this? Well, the idea is to compare this expression with the potential, with the quantum correct Newtonian potential obtained by John Donogh and collaborators, and not only John Donahue or Donogh, I don't know what is the correct pronunciation.
Donaghy.
Okay. Okay, thanks. Anyway, okay, let me tell you fastly how. What is this? What are the core of these ideas? Essentially, Donahue in the first paper is 94, and then there is a sequence of papers arriving to our ears. The idea is the fact that general relativity can be seen as a low energy effective field theory. At ordinary energy, gravity is a well-behaved quantum field theory, so you are ignoring, so to say, of course, the fact that in principle general relativity is not a normalizable theory, but you stay at low energy. So the quantum corrections at low energy and the dominant effect at large distances can be isolated, so to say, so that the potential energy between two EV objects close to rest can be written at the first order, at the lowest order in the correction in H bar by with an expression, the potential of this kind. in particular this coefficient here. And then, of course, if you compare this expression came from this Donnelly approach to the expression of the potential computed using the ASG ideas, you can compare it and immediately you can fix the omega tilde. The omega tilde, in this case, will be this number here. Let me tell you first, very fastly, how you can fix gamma, the other parameter. The gamma parameter actually cannot be fixed immediately from the previous considerations. There are general relativistic arguments proposed by, in particular, by Bonan and Reuter in 2000, so that these arguments brings to the value of 9.5 for the gamma. Other considerations from the GUP, the generalized uncertainty principle consideration, can bring to gamma equals 0. In any case, we have considered models with gamma larger than 6 essentially. But for even most important for our consideration is the sign of the first order correction in H bar. I mean this object here, this computed which is immediately reflected in the sign of omega tilde. It's crucial for the physics of this ASG improved method. To my knowledge, the first correction in H bar has been computed with the spatial metric, or if you like, the Newtonian potential, has been computed by Duff in '74. He got an H bar term coefficient positive, and therefore we would have an omega tilde negative. The early calculation of the Donahue in '94 until 2003, they showed an H bar coefficient negative and therefore a non-negative positive. And actually this was the coefficient used in the first paper on this stuff written by Bonan and Reuter in 2000. So they based their analysis on this calculation, Donahue. And the consequences are pretty nice from the geometrical point of view, because you get a metric which is singularity free with a de Sitter or anti-de Sitter core. However, we should say that starting from 2003, all the calculation made by this community, Donahue and Kripovich, and so on and so forth, until the last paper published about 9 months ago, in January of this year, so very recent, by Freud and collaborators, they all get results coherently point to a positive H bar coefficient, which means a negative value of omega tilde. And this has some deep consequence on the structure of the black hole network. Which are these consequences? Okay, here you are. Here you have the consequences. Okay, so let's consider omega negative, gamma strictly positive. Our lapse function is this. And now here we have a minus sign, clearly a minus sign. This means that this denominator can develop zeros, and therefore the metric can have singularities. In particular, we have shown that the lapse for any value of the parameter for R positive, gamma positive, and the mass also of this object obviously positive, as one real positive zero, this denominator, so one essential singularity at R0 greater than 0 here. This is a new thing in respect to standard Schwarzschild. Usually this singularity for Schwarzschild is at the center, at radial coordinate equals 0, and here we have instead a positive value of this radial coordinate. As for the horizons, we have shown that you have only one single positive zero of the usual equation, which fixes the horizon. So our black hole, our ASG black hole, has an horizon at this point here. So here you have RH, here you have R0. It is interesting that R0 is always, for any value of these parameters, smaller than RH, so we do not have naked singularities in full accordance with the cosmic censorship conjecture. Let me tell you a little bit about the behavior of these two numbers for large mass or small mass of the collapsed object. In particular, for when m goes to infinity, for large masses, we recover the standard Schwarzschild horizon. When, on the contrary, m is going to 0, very small, then we have the horizon as an expression like this. You see that for vanishing mass, you still have a kind of horizon, but this horizon is essentially at the Planck, as a radial coordinate equal to the Planck length, which, physically speaking, is quite reasonable, since any length below the Planck length, any region below the Planck length, in principle, cannot be explored, is physically meaningless. So it's not so bad if your horizon, even for zero mass or vanishing mass, stay at the Planck length from the origin of the coordinate. It's interesting that the behavior of the coordinate fixing the place where the singularity is. For a vanishing mass, you have an expression like this. So this singularity places more or less at the end region of the Planck, at the Planck scale, essentially. But more important and more interesting, at least for us, was the fact that when m become large, so to say, in respect to Planck mass, essentially, then the singularity behave in this way, like the cubic root of the mass itself, plus some corrections. Oh, by the way, we can note that in both limits we have always R0 smaller than RH, so singularity results always protected by the horizon. Maybe a little, the situation can be illustrated a little bit more by looking at the mass functions for the horizon and for the singularity. The red line here is the mass function for the horizon. You see that for large R you approach essentially the mass function of Schwarzschild. Schwarzschild is the green line. The blue line is the mass function for the singularity. In Schwarzschild you would have just this vertical axis, of course. Here you have this blue line. Which is going for large R, essentially like R cube. What can we say with this particular behavior of R0? Well, as we have seen, the central singularity is located at this place, which is a number greater than 0, scaling as the cubic root of the mass, contrary to Schwarzschild, where R0 is 0. The finite size of this object is fully of quantum origin. In fact, if you push h bar to 0, you go back to the standard Schwarzschild location of the essential singularity. And well, you can imagine that the whole collapsing mass can be thought as concentrated into the central hard sphere of radius R0, and you can compute the non-covariant volume of this sphere as seen by a far observer of infinity, and therefore you can compute the density of the matter collapsed into this sphere of finite size. And this density results to be finite. And apart from some numerical factors, is essentially the Planck density. So one Planck mass over one cubic Planck length. Well, therefore, the metric describing our black hole, the metric that I've shown you, this object here, this lapse here, as essentially exactly the characteristics of the so-called Planck stars, which were proposed by Rovelli and Vidotto some years ago, in general, so on the basis of quite general qualitative considerations. Well, here you can see that the finite size of this central core of our black hole, being of pure quantum origin, presumably can be thought to be due to the action of the Heisenberg uncertainty principle, which prevents matter to be arbitrarily concentrated into a geometrical point of size 0. The central kernel of this black hole can in principle keep trace, perhaps, of the information swallowed by the black hole. So perhaps this can be at least investigated as a possible way out from the information paradox. Of course, these considerations are valid for gamma strictly larger than 0. I'm arriving to my last but one slide. Let me compare this metric that we found with the previous one proposed, in particular by Rovelli and Vidotto, for describing this Planck stars object. Well, there was an original educated guess to describe this kind of object. The metric chosen was the Hayward metric, which is a singularity-free metric. Actually, this was the only interesting quality of this metric, where there were no particular other compelling argument in order to choose a metric like this. However, this metric has two problems from our point of view. The first problem is that if you expand in R, you do not have the term 1 over R cubed for large R expansion, which is the one that you need to match the quantum corrections computed by Donahue and collaborators to the Schwarzschild metric. And the second problem that a metric like this can have is the fact that I'm almost finished. Is the fact that, okay, for large n, take a large mass, you have the metric develops two horizons. The external horizons is nice, it goes smoothly to the standard Schwarzschild horizon. The inner horizon, I would say unfortunately, just go to a fixed value, L, and even assuming these R minus as the size of the other kernel of a Planck star, certainly such other kernel does not increase in size with an increasing m, as instead R0, the R0 that we have computed before, does. Some people working in this Planck star business, they have tried to cure these problems of the Hayward metric, but well, this can be done, but at the price of much more complicated lapse function, introducing essentially by hand a correction like this. While, well, on the contrary, we have seen that using the metric suggested by the ASG approach, we just get the central, the radius of the central hard kernel for free, essentially, and in the correct value, so to say. So I'm going to my conclusion. The ASG approach suggests a general metric describing the quantum effect containing H bar. The matching of this ASG corrected metric with value quantum correction to Schwarzschild metric dictates a negative value for the omega t parameter. This negative value implies a new geometry for the ASG black hole metric, the prediction of a finite size singularity at the core of this black hole. The size of these black core, so to say, describes exactly so-called Planck stars, which were introduced via semi-qualitative arguments some years ago, while on the contrary, in this context, they appear as a natural mathematical consequence of this ASG metric with this omega tilde negative. These objects, the Planck star, they have a quite rich phenomenology, which absolutely I will not discuss here. Just a brief list. Probably you can consider black hole evaporation with a final explosion occurring at scales much bigger than the Planck scale. They can be quite naturally associated with short gamma ray bursts. And even also there are works dealing, connecting the Planck stars object with the fast radio burst of extragalactic origin, with wavelengths close to the expected size of this exploding object. Okay, this was my last slide, so thank you very much for your attention.
We have time for one or two questions.
I think one should perhaps say that while the general asymptotic safety computations, that's really quantum field theory very well defined, there is a certain amount of guesswork when you try to translate the scale K to a metric. There is no diffeomorphism symmetry visible anymore. So one should take these things with a little bit of caution. What comes from the guesswork and what comes from, let's say, more solid calculations.
Things. We are aware of this. So to say, the weak point of this kind of approach is exactly this fixing of K of R, this function, which is somehow interpolating the behavior of this K for small r, but it's a guesswork. I agree 100%.
We have one more question? One more question. Over here? This? Okay.
The value that you found, the 41, the pi, that was according to the updated calculation of Donny, or the older one?
No, this is the modern value. That's the switch. In the old papers, Bonanno and Reuter and so on, they used the value computed by Donahue in 94, 95, which had a negative sign, and therefore they get an omega positive. On the contrary, from 2003 to now, practically all the approach, all the different calculation brings to a positive coefficient of h bar, and therefore a negative value of omega. So this is the last value that we get in literature, so to say.
I don't know, but let us first thank